Marc-Antoine Miville-Deschenes, who's going to tell us new results from Planck on galactic dust.
Hello, everyone. So I wanted to show this beautiful image of Planck that was released very early in the mission. It's really showing the complex structure of the interstellar medium and its link with the activity of star formation. So the talk will be about trying to model this emission over the full sky. This is what we attempted a few months ago, and it's a product that we have been released with at the same time as the Planck data. So just a few words about the model of dust emission. Well, the goal of this project was to produce an all-sky map of dust optical depth, and this all-sky map can be used to study the structure of the interstellar medium from all gas phases. So that's very important. Rod made a very thorough review of all the interstellar processes that we see with the Planck data, and we see emission coming from the ionized phase, the atomic phase, and molecular clouds. The good thing about dust emission that is, we think, well mixed with the gas, and so it traces the full amount of matter on the line of sight, unlike all the other processes that are specific to some phases. So it's really, dust is really providing an information on the structure of interstellar matter, and Planck, with its resolution and sensitivity and spectral range, can do that better than we could ever do it before. So the goal is to produce this structure, ISM structure map. It also gives a full sky map of the reddening, the EB minus V. Some of you might be aware of the Schlegel et al. Map from 1998 that was extensively used for reddening estimate on extragalactic studies and cosmology studies. So with the Planck data, we can produce a better map than what Schlegel did, and that was one of the goals of this project. It's also interesting to evaluate the shape of the dust SED in a frequency range that was not observed so much, well, not over the full sky, and it tells us also something about the dust emissivity. It's all written in the top right corner equation. So the emissivity as a frequency nu is proportional to the Coulomb density of atoms, the Planck function that is related to the equilibrium temperature of the dust, and this alpha and nu beta coefficients that is giving information about the dust emissivity, the efficiency of dust to emit radiation. So by modeling the dust emission, we have access to all those information, but we have to disentangle the effect of temperature, the dust emissivity, and Coulomb density. So that's the difficulty of the task. It would also provide an improved dust model for component separation, obviously. So as I mentioned, the advantage of Planck is this higher angular resolution, the frequency coverage. But the frequency coverage is very important because to estimate the optical depth, you're dependent on the estimate of the temperature, as you see in this equation. And going at longer wavelength, an error on the temperature has less an impact on the opacity you measure. So as an example, if you estimate the opacity at 353 gigahertz, an error on temperature of 1 Kelvin, which is a huge error on temperature, implies an error on opacity, on optical depth only of 6%. If you do the same thing at 100 micron, you get an error of 30% on the opacity. And that's how Schlegel et al. Did their work, and that's how it was done before. So we improve a lot the precision on which we can estimate the total Coulomb density. So I will talk a lot about dust optical depth. It's really the intensity at 353 gigahertz divided by the Planck function at 353 gigahertz, estimated the temperature T. So just a few words about related previous work. I talked a lot about Schlegel already, where they assume a constant beta of 2 over the full sky. They estimate temperature using Derby, degraded at 1.1 degree resolution using 100 micron and 240 micron. And they estimated the opacity, the optical depth tau, using the 100 micron RS map at 6.1 arcminute resolution. There's also the work of Finkbeiner et al. In '99, which is important because it's really how we are modeling dust emission. It's the main model that is used in the Planck sky model for now. And so it's a combination of two dust components, one with a beta of 1.67 and one with a beta of 2.7. So I'm showing two models here. They're basically equivalent, but so there's a high beta component, 2.6 or 2.7, and a low beta, 1.5 or 1.67 component in their model. We have not followed that route of trying to model the dust emission with two dust components. It has no physical ground to do this. Everything we know from dust physics is not compatible with a low beta, low temperature, a high beta, high temperature. So we decided not to follow that route. I have to mention the work we did in 2011 on the Planck early papers, and at that time the beta we were estimating was 1.8 between 353 gigahertz and 100 micron, and the temperature was 17.7 K. So on the top right here is a full sky map of the dust temperature estimated at the time using IRAS and Planck data. I will come back to that later. And one important point that came out from those early papers is that there's an increase of dust opacity as function of NH. So it's shown here. This is the dust opacity at 545 gigahertz as function of column density estimated from gas tracers. And so there's a correlation, but there are deviations from the single line that you expect if dust properties are constant. And that was interpreted as the sign of dark gas, so molecular gas, dust in molecular gas that is not emitting in CO. Or it could also be caused by an increase of the efficiency of emission of dust grains. But this was clearly showing that there was something going on between dust and gas, and that we need to take that into account. So the methodology of this model is, well, just one word that was not highlighted so much in this conference, but one important point that happened with this new data release compared to the data we used for the 2011 papers is the recalibration of the two highest frequency channels. 857 went down by 7%, and the 545 went down by 15%. And that has a very important impact on the properties of dust we are estimating, because those channels are really dominating, are very important in the model of the fit, in the model of the dust acidity, and so it has an impact on parameters, especially T and beta. So the values I gave you in the slides earlier are going to be revised, and I warn you that they're quite different than they used to be. So the methodology is so that to do this model, we really need to have a reference of the map. The zero level of the map is very important because we're fitting the data pixel by pixel. So we had to set a galactic reference for each map. We remove point sources to produce an EB minus V map without galaxies. We remove CMB in the map, and so we are fitting the dust acidity using two methods. One is using the Drain-Lee 2007 model, and this is work that is in preparation. That would be part of another paper, and the work I'm presenting here is using a modified black body fit at each sky position. So we're taking into account instrumental noise and gain uncertainty in the fit, and that's really important. So just a few words about biases on the modified black body fields. You might have heard about anti-correlation between T and beta. So we have extensive inner galaxy, and that's the next map. So that's the map of the spectral index beta, which is now 1.63 on average on the sky. So it's significantly different than 2, significantly different than 1.8. So here's the histogram of the beta index over the full sky, and that's the value that we use 15 years ago, and that's the value we use for the Planck early paper, and that's the histogram of the beta value now. And the main change is, again, it's due to the recalibration of those two channels. The statistical error is very low, as you can see. So it's very well estimated. You can see some fluctuations at high latitudes around here and there. Some small noisy structure in the beta map. This is caused by the CIB anisotropies. They are in those maps, and they are correlated in frequencies, and so they are biasing the estimate of the dust parameters. But this is also causing an impact on tau, which is quite low. So one important product that is released with those maps is the reddening map, the EB-V map. And to obtain that, we do a correlation between SDSS reddening measurements of quasars. So we're using a sample that is almost 55,000 quasars to correlate the reddening measured by SDSS to the dust optical depth measured by Planck. And so you see that on a decade in column density, we have a very, very tight correlation between these two measurements. And so this has to be compared with the Schlegel method that they use a similar approach to estimate EB-V to translate opacity into EB-V, and they use only 472 elliptical galaxies in their sample to do that. So this 100 times more samples, and it's very, very, very tight correlation. So we have great confidence in this correlation. So it's providing a very precise EB-V map. It's compatible with Schlegel at 6%, at the 6% level, and which is compatible with their uncertainty on EB-V. What's interesting is that the correlation is very straight over a factor of 10 in column density, where we go from diffuse ISM to almost molecular clouds. Molecular clouds, start to appear. Well, you see molecular gas in this at this type of column density, and here you enter into a molecular clouds regime, and we don't see any departure from a straight line between extinction of dust and emission of dust. So that's in accordance with a rather constant average dust properties in the diffuse ISM. So a few words about that. One of the important results we had from the early papers is that we were seeing variations of the dust emission compared to the gas tracers, and so we know that this is one cause of that is the presence of dark gas. And so I recall this graph from the early papers where we were measuring the fraction of molecular hydrogen in the gas as estimated from dust emission as function of column density, and so the black dots here are Planck measurements, and the triangles and squares are from UV measurements. And we see that at a column density above 3 times 10 to the 20, we start to see appearing molecular gas in the ISM, and Planck and UV measurements were compatible. So that was done on specific small fields. Now we can do that for the full sky, and that's the top figure so it's not fraction of H2, but it's the emission of dust compared to the column density of H1. So when you have an excess in this value here, it's because there's dust coming from another component than H1. So above 3 times 10 to the 20, again, we see this increase that is related to the appearance of molecular gas. And what's new is an increase at low column density that we attribute to dust from the warm ionized medium. And so that's something we were really, really looking for. And it was very difficult to find in previous data sets, and in the Planck data, it's coming out very nicely. So just a few words now about molecular clouds. This is a map of the dust optical depth in the chameleon molecular clouds, and on the right you have a map of the dust temperature. So again, these two maps are at 5 arc-minute resolution. It's the first time we have a map of dust temperature at that resolution. The Schlegel products was at 1.1 degree resolution. So it's a huge gain in the structure and in the physics of molecular clouds coming from the Planck data here. And it's also providing a new basis for the model of dust emission, because we can really trace the evolution of dust to such small scales. On molecular clouds, one other interesting thing is to compare emission and extinction again. As I showed you earlier, in the diffuse ISM, there is no departure from a linear relationship between the two. But when you enter into molecular clouds, that's not true anymore. So here is Planck EB-V as function of EB minus V estimated by 2 mass, so it's EJ minus K translated to EB minus V. So if the emission and the extinctions were this, if we were okay with the conversion we use in the diffuse ISM, you expect a 1-to-1 correlation here, and the slope is 1.57. So there's clearly an increase of emission as per extinction in molecular clouds, and that's just one example. All the molecular clouds we've looked at as similar behavior. This is compatible with what we had in the Planck early papers. This is not a new result, but it can be done on very systematically and with much more precision than before. So this is a complicated graph. So, but I will try to explain that in just 20 seconds. This is the over the full sky. You can do statistics on beta and on temperature. And when you bin all the pixels on the sky into bins of column density, that's what you get. So on here, if you follow from the top, from the middle right here, it's very low column density on the sky. So that's the average temperature, average beta you measure in very low column density, and you see that there are trends here. This is basically the branch of the warm ionized medium. This is the diffuse ISM and the molecular clouds, and that's the inner galaxy, where you clearly see an increase of the temperature, and as at the same time you see an increase of beta in the inner galaxy. So it's not true that we have an anti-correlation of beta and T everywhere on the sky. And so there's a lot of information to come out to be digged out from that, and so that's still work to be done. It's just an exploration for now. So in the minute I have, I just want to say a few words about the spectrum of the dust at lower frequency than 353 gigahertz, but because this is of interest for cosmology, so also interest for dust. This is dust SED estimated at high latitude in the very diffuse ISM by correlation with H1, and so it's at the bottom it's always the same SED. On the top it's just the difference with the model depending on which band you use to estimate the SED. On the left you make the fit from 100 micron to 353 gigahertz, and you end up with a spectral index of 170 in this case, and a clear excess at so it's compatible with the flattening of the dust SED at longer wavelengths. But if you use the full frequency range to do that, you get 1.55. So that's it tells us that if you do the fit with 2 beta, one at high frequency and one at low frequency, you get a better fit. Even though here the chi-square is below 1, you get a better fit here with 1.65 here, which is the value we have at high latitude, and 155. So it seems that there is a flattening from slight flattening from 165 to 155. Thank you. That's my last slide, and that's shown here in the commander ruler results, where they estimated the dust spectrum exactly in that frequency range between 353 gigahertz and 100 gigahertz. And so that's the map of the spectral index they have. This is a map of the spectral index at higher frequency that we get out from the modified blackbody fit. So you can see that there is a similarity between the two, but it's the same color scale, so there's a clear shift between the two, and these are histograms of the beta. So there seems to be a significant flattening of the dust SED. So I'm just skipping that. So that's just to announce the products that are on the Planck archive, and just to mention a few results. The main message you need to get out of that is that we are re-estimating the temperature of the dust and the spectral index. It's really different than what it was before. It doesn't seem to. Maybe you don't think it's a big deal, but for us it's a big deal because it changes a lot of the dust physics. We have to go back to our models and see if they are compatible now. And we are seeing some significant differences, and so it's opening new avenues for dust physics now. Thank you.
Thank you, Marc-Antoine. Great new results there from Planck. Time for some questions.
Hi, a comment and a question. The comment is that we've carried out a similar although less extensive investigation of the dust in the other big spiral in the local group, M31, with Herschel. And we too find a change in beta towards the center. So it's kind of interesting that there's a similar result. The question is, if you look at tau over NH1, do you see any evidence for that varying as you go out along from the to high longitudes, as you go out from the galactic center? Because if there's a metallistic gradient, you might expect that. If a constant fraction of metals are in dust grains, then you sort of expect there to be some gradient.
Yeah, that's what you expect. I'm just trying to remember that map. I've looked at that map so many times, this tau over NH map, and so it's not so clear to me that there's a huge effect going from inner galaxy to outer galaxy in this ratio. No, I don't recall seeing that so strong an effect, but we can discuss that later.
Yeah, well, if there isn't, then that tells you something about how dust is formed, so it's kind of an interesting result.
Yeah.
So the high latitude dust map's now gone for a resolution of just over a degree, I guess, and the Schlegel map's down to 5 arc-minutes, is that right?
The temperature that is used to estimate the dust column density, you remember there's a Planck function in this equation, so that is at 1 degree resolution, the temperature. But
on the sky, angular resolution.
The angular resolution, yeah, that's right. That's
right.
Saying.
So when you look at the structure at high latitudes, how much additional variation do you expect to see going down to the scales when this is actually applied extragalactically, which is usually a few arc-seconds for most extragalactic objects? So do we expect still to be considerable variation on scales smaller than 5 arc-minutes?
Well, if you follow down the power spectrum of dust, it's we know from Herschel data that this minus 2.6 power spectrum of dust is going down to the spire to 50 micron resolution. Yes.
Time for one last quick question. Okay, we've got a question here.
Yeah, in these maps I'm always amazed by this minimal 15 Kelvin temperature. Now this is just a little bit above the 13.8 triple point of hydrogen. And do you know whether there have been made connections to that? Somehow there is some hydrogen which thermostats this dust?
I'm not aware of any studies on this. No.
Okay, we'll talk it over later.
Okay, let's thank Mark and Twan again.